Hello everyone. So in this numerical, they have given two MOS transistors connected in series with channel lengths of L1 and L2 and identical widths of W. So now can be modeled as one equivalent MOS transistor whose width is W and whose length is L1 plus L2. Ignore body effect and channel length modulation. Okay, so we have to model this equivalent of this series connected transistor as this. Okay, so before we prove mathematically, we need to analyze that what are the operation region of operation of both transistors. Okay, so suppose there is a NMOS. So this gate drain. So what will be VGS? VGS will be VG minus VS. Okay, so we now add and subtract VD. So VG minus VD plus VD minus VS. So this will be VGD plus VDS. So this KVL is true for NMOS. So VGS will be VGD plus VDS. Now for NMOS to be in saturation, VGD should be greater than VGD should be less than VTH. Okay, then saturation. Now let's check for M1. So what will be the voltage? This one. This one is VGS2, and this one is VGD1. So in this loop, we can say that VGS2 is VGD1. Okay, and if there is current flowing, then M2 is turned on. So that VGS2 must be greater than VTH. Okay, so this is greater than VTH. So from here, VGD1 greater than VTH. So if there is any current flowing through M2, then M1 will always be in linear region. Okay, so always in linear region. So we can also calculate V over drive, and that way we can prove. So what will be the VDS1? From this KVL, VDS1 will be VGS1 minus VGD1. VGS1 will be V over drive 1 plus VTH. Okay, and minus VGD1 is VGS2. So this one will be V over drive 1 plus VTH minus V over drive 2 again minus VTH. So this will be cancel out, and this will be V over drive 1 minus V over drive 2. So see here, there is something reducing from V over drive 1. So it's less than V over drive 1. So VDS1 is less than V over drive 1. From here also, we can say that M1 is in linear region. Okay. So is there any condition that makes both transistor as in saturation region? So suppose VTH1 not equal to VTH2, then what will be the VDS1? VDS1 will be VGS1 minus VGD1. So VGS1 will be V over drive 1 plus VTH1. Okay, and VGD1 is VGS2. So this will be V over drive 1 plus VTH1 minus V over drive 2 plus VTH2. Okay, so this will be V over drive 1 plus, suppose I'm saying VTH1 minus VTH2 is delta VTH. Okay, so delta VTH minus V over drive 2. So if this value is positive, then something is added positive to the V over drive 1. So VDS1 will be greater than V over drive 1 and M1 can be in saturation region. So if this condition is true, then M1 can be in saturation region. Otherwise, if they have equal VTH, so they won't, then M1 will always be in linear region. Now how let's prove mathematically. Okay, so connection is like this series connection. This one is VDS1. This one is suppose VDS, and this one is VGS. Okay, and this one is VGS2. So suppose this current is I2 and this one is I1. So they are in series. So I2 will be I1. Okay, and what will be I1? Since M1 is always in triode region, so I1 will be linear equation, like linear region current. So what will be the I1? I1 will be mu1 Cox W by L and VGS1 is VGS minus VTH into VDS1 minus VDS1 square by 2. Okay, so this current is flowing through this M1 transistor, and this equal to I2 always, because they are in series. So current must be same. So let's solve this equation. So this will be mu1 Cox W by L1 VGS minus VTH into VDS1 minus VDS1 square by 2 minus I2 equal to 0. Okay, now let's solve again. VDS1 square by 2 plus VGS minus VTH VDS1 minus I2 by mu1 Cox W by L1 equal to 0. Now again what will be the multiply whole with 2. Okay, so VDS1 square plus multiply by minus 2. Okay, so it will be VDS1 minus 2 VGS minus VTH into VDS1 minus plus 2I2 divided by mu1 Cox W by L1. Okay, equal to 0. So this is value of VDS1. So we will solve for VDS1. So what will be the, this is similar to like AX square plus BX plus C equal to 0. So root of this equation is VDS1 will be 2 times VGS minus VTH plus minus root over B square minus 4AC. So it will be 4 VGS minus VTH whole square minus 4 into 2I2 divided by mu1 Cox W by L1 divided by 2A. So 2 into 1. Okay, now so since we know that M1 is in linear region. Okay, let's simplify one more step. So it 2 will cancel out. So it will be VGS minus VTH plus minus root over VGS minus VTH whole square and 2I2 divided by mu1 Cox W by L 1. Okay, that 2 will come out and cancel with 2. So now we know that M1 is in linear region. Okay, so VDS1 must be less than VGS minus VTH. So what will be the valid root? Valid root would be taken by minus sign. Okay, so we will take minus sign. So here VDS1 will be VGS minus VTH minus root over VGS minus VTH whole square minus 2I2 divided by mu Cox W by L into 1. So this is the value of VDS1. Okay, now so this will always be the VDS1 for because NMOS is in linear region. So this is correct. Now there can be two possibility. Either M2 can be saturation region or linear region. Okay, so now let's case 1 M2 is in saturation region. Okay, so what will be the current flowing through M2? It will be I2 so this current will be 1 by 2 mu1 Cox W by L VGS2 minus VTH whole square. Okay, so I2 will be 1 by 2 mu1 Cox W by L to VGS2 minus VTH whole square. Okay, so 1 by 2 mu1 Cox W by L to what is the VGS2? VGS2 is what is here VGS2? VGS2 is VGS minus VDS1. Okay, so VGS minus VDS1 will be this one VGS2. Now put this value in this equation. So this will be VGS minus VDS1 minus VTH whole square. And now again 1 by 2 mu Cox W by L 2 and this one is VGS and what we calculated just above VDS1. So this one is VDS1. We will put that value here. So VGS minus VTH and then minus minus will be plus root over VGS minus VTH whole square minus 2I2 divided by mu1 Cox W by L 1 and minus VTH square. This VTH. So this VGS cancel. This VTH plus and this one cancel out. Now what will be the left? 1 by 2 mu1 Cox W by L 2 and this will be left and there is a square. So this will be VGS minus VTH whole square minus 2I2 divided by mu1 Cox W by L 1. Okay, so this is value of current I2. Now let's take I2 to the one side. So this is I2. So this one 1 plus what will be the this will come out. So okay, let's simplify one more term. So this will be 1 by 2 mu1 Cox W by L 2 into VGS minus VTH whole square, and then minus, so this will 2 will cancel out this one, mu1 Cox, this mu1 Cox will cancel out, so we will left with I2 into W by L 2 divided by W by L 1. Okay, now take I2 together. Okay, so this one I2 1 plus W by L 2 divided by W by L 1 equal to 1 by 2 mu1 Cox W by L 2 VGS minus VTH whole square. Okay, now what will be the I2? I2 will be 1 by 2 mu1 Cox W by L 2 divided by 1 plus W by L 2 W by L 1 into VGS minus VTH whole square. Okay, now W is same L1 L, and there is for M2 L2 and M1 length is L1 and width is same. So this will be 1 by 2 mu1 Cox, and this will be W by L2 divided by 1 plus W will be cancel out, and it will be L1 by L2. Okay, into VGS minus VTH whole square. Now 1 by 2 mu1 Cox, this will be W by L2 into L2 divided by L1 plus L2. Okay, now this is VGS minus VTH whole square. Now again 1 by 2 mu1 Cox L2 cancel out, this is W by L1 plus L2 VGS minus VTH whole square. Now here you see this one is I2. So this equation is representing there is the I2 current flowing through a transistor which have W by L1 plus L2. Okay. So we proved that if M2 is in saturation, and so we can model as a single transistor with width of W and length of L1 plus L2. Now in case second, so we won't prove case second, you can try by your own. Okay, so only you think you have to do is you have to put I2 equation as, now the M2 transistor is linear region. Okay, this I2 is linear and I1 is already linear. It will always be in linear. I2 now is linear region. So what will be the I2? I2 will be mu1 Cox W by L 2 into VGS minus VDS1 minus VTH. Okay, into VDS minus VDS1. This one is VDS and this one is VDS1. So mu1 Cox W by L2 VGS minus VTH into VDS1 VDS2. Okay, so like VGS2 minus VTH into VDS. So VGS2 is VGS minus VDS1. Okay, so VGS minus VDS1 is VGS2, and VTH into VDS minus VDS1 will be VDS2. This voltage will be VDS minus VDS1. Okay, so I'm minus VDS2 square by 2. So and VDS2 is VDS minus VDS1 square by 2. Now here put that VDS1 value we have calculated above. So this value, VDS1 of this value, we have to put in this equation, and again when you will solve, you will get the same equation, same model as it will come as I2 equal to mu on Cx W by L1 plus and VGS minus VDS1 square minus VDH. This one will come out. Okay. VGS minus VTH into VDS minus VDS square by 2. Okay. So I2 is mu on Cox W by L VGS2 minus VTH into VDS. So VGS2 is VGS minus VDS1 will come at this VDS2. Okay. And VDS2 is VDS minus VDS1, and VDS2 is VDS minus VDS1 square by 2. So when you put that VDS1, you will get this one equation. So in both case, we can model this transistor as W divided by L1 plus L2. So again, in summary, so this M1 transistor will always be in triode region. M2 can be in linear region or saturation region. So in both case, whether it's in linear or saturation, we can model both transistor as equivalent as W by L1 plus L2. So we just prove by mathematically also. Okay, so if you have any doubt or you didn't understand, you see any wrong calculation, then let me know. Okay, so this type of question are very frequently they asked in interview, like series combination, parallel combination, and this structure is known as Poor's-Man. Okay, Poor's-Man cascoding, because it's not both transistor are not in saturation, because in cascoding we usually say both are in saturation region. So, but it serves the purpose of cascoding, but it's not actually cascoding. Okay, so thank you.